Haven't done music in a while. Woo! All right, folks, we're getting into this chapter on solids, and I just kind of felt like hard rock and roll talking about the solid state. Okay, let's turn this off. Woo! Okay. All right, enough of that. I felt like rocking out. There's just something about thinking about solids and making me want to listen to some hard rock. Okay, so let's get into it. So this chapter is going to be a lot more conceptual, qualitative than our previous chapters. So a lot of definitions, as you can see, and a lot of what we call descriptive chemistry. Okay, so let's get into it right away. So some of these definitions, I'm just going to kind of go through these definitions, and then we're going to see how we can apply these definitions and our understanding of the physical world. So crystalline solid, first one here to think about. Let's make that a little bit thicker. So crystalline solid, a solid made of an ordered array of atoms, ions, or molecules. The most important thing there is ordered array. So we're going to see like a repeating unit of atoms, ions, or molecules. Okay. So we have an atomic solid, and this is a solid formed by single atoms covalently bound in either an organized network, so that's specifically a network solid, or at discrete lattice points, and that's specifically a metallic solid. So the important thing about this definition, for one, single atoms, so things like iron or carbon or silver, okay? And we shall see that those atomic solids can either form a network solid or a metallic solid, okay? So even more specifically now, our metallic solid is a solid formed by metallic bonds amongst atoms of metallic elements. Or we could have an atomic solid that could be described as a covalent network solid. And in this case, this is a solid formed by covalent bonds amongst non-metal atoms in some type of an extended array. Okay, so that's our principal difference between the two types of atomic solids. One is metals, the other is non-metals. And as it turns out, the non-metals make this rather interesting covalent network that we will see some examples of soon. Okay, so we can also have an ionic solid. And so that's a solid consisting of monoatomic or polyatomic ions together, held together by ionic bonds. And so the important thing is here we have to have a cation and an anion, right? So think about your qualitative analysis. You're primarily dealing with ionic solids, right? You are precipitating a cation with another anion, okay? So we could also have a molecular solids. So these are solids formed by neutral, also covalently bonded molecules held together by intermolecular attractive forces. So I'm going to say IMF, such as H bonding or London dispersion forces, okay? And so a classic example of molecular solid would be ice, right? It's made up of water molecules all held together by hydrogen bonds. And then the last type of solid we'll explore is an amorphous solid. And that's a solid that lacks any long-range order of atoms, ions, or molecules in its structure. So we won't do too many examples of these, but glass is a really good example of an amorphous solid, okay? So let's continue along and see. I've got examples here, and we'll describe what kind of solid it is and talk a little bit about the physical properties. Okay. So here I've got xenon, only xenon, so we can tell that's an atomic solid held together by atoms. So class is atomic, particles are atoms. So our electrostatic attractions, so what's keeping the xenon atoms together, I'm going to say LDF. That's London dispersion forces. And these types of solids, these types of atomic solids, have quite a large range depending on what it is. But mostly for the atomic, so in other words, the non-metallic atomic solids, okay? So typically have low melting point, okay? They're poor conductors. They're soft, so we'll say poor conductor. So I couldn't make a conductor out of xenon atoms. On the other hand, if I had silver atoms, okay, notice now there's a very similar, so this is it's still an atomic solid, but specifically I would call it a metallic solid held together by atoms. So the attraction, what's keeping the particles together, is metallic bonding. And these will have much higher melting points. I can't talk. Higher melting point. And because I'm writing so terribly and I can't write small enough, I'm just going to describe these physical properties orally. So these things can be quite hard. They're excellent conductors. So these are metals, right? Okay. So now our next example, carbon, and specifically in a diamond. And now if we look at the way that this is all structured, this is a covalent network solid, okay? And it is held together by atoms, okay? These are covalent bonds. So we can see each little carbon is bonded to another carbon from covalent bonds. And these types of solids have very high melting points. They're very hard. They're not good conductors, okay? So poor conductor, but they are very hard. So it's a diamond, right? It's one of the hardest materials that we know about. And they have a very high melting point. Okay, so sodium chloride is a good example of an ionic solid held together by ions, cations and anions. So that is ionic bonding. And if we were to describe their physical properties, so this is salt, right? It's table salt. So it has a very high melting point, right? When's the last time you were able to melt a cube of salt, right? It's got an extremely high melting point. These are actually good conductors when molten. So I'm going to write good conductor when melted. And so what that means is when it's become a liquid, which is hard to think about, right? But we could melt sodium chloride into a pure sodium chloride liquid. Now those charges are separated, and it can conduct electricity really well, okay? And so these are also very brittle. So I'm going to write brittle. And what we mean by that, it's not very flexible. So on the other hand, our metallic solids can be quite flexible. If you imagine like taking a metal bar and bending it, you have to be quite strong to do that, but you can totally bend a metal bar and it will stay intact. But a salt cube like that, if you tried to bend that, it would just snap, okay? Okay, so moving along. So now these are examples. So S8 and CO2 of molecular solids. So in fact, all of these are good examples of molecular solids. H2O, Cl3, CO2, and S8. All of these, okay? And so these particles are all molecules. And now the electrostatic attractions amongst these molecular solids are quite variable depending on what this is made up of. For example, the ice is predominantly H bonding, whereas the CHCl3 is predominantly London dispersion forces, and also a little bit of dipole interaction because this molecule is polar. And S8CO2 will also be principally LDF. And now the physical properties of all these molecular solids are quite variable. But one thing they do all share in common is they are typically poor conductors, they're soft, and they have low melting points. So once again, if you kind of think about ice compared to like iron, right? Ice is very soft. You're not going to be able to build a building out of ice, right? It's also not a great conductor either. Okay. And so finally, the last actual example I'll describe is an amorphous solid. There it is written right there. And so, for example, obsidian or volcano glass, SiO2. And this picture might be difficult to see, but there's no real order or crystal structure to this particular type of solid. So that's what makes it amorphous. Okay. So I realized this was a little sloppy. So these physical properties are described a lot better in table 12.1 in your book. So take a look and read more about these descriptive properties if you feel like you didn't get enough info from the slide.